Broadcast is now starting. All attendees are in listen-only mode.
Okay, good afternoon, everybody. This is Dr. Mansour, and today is March the 7th, and this is the surveying review, or the review for the special surveying exam. According to the course outline, or our brochure, or our website, today is the Saturday. This is meeting number 5. Today is 3/7, or the 7th of March, and between 4:30 to 7:30, and I call it workshop because those who are enrolled in the class, they have access to the on-demand 24/7. I hope that you are getting benefit from all these things because the 50-hour class recorded for you and it's available for you 24/7, and I'm here to help with any questions or any concept or any material that's not clear to you. Okay, we still have one more session in this quarter, which is session number 5, and this is on the 28th of March at the same time also. So let me bring my books here and start to ask or which chapter you want me to go over it, or which problem from the 497 or the practice exam book, or my textbook, which is this one here, the surveying practice, surveying for California, the 15th chapter. So these are the 3 books. The summary book, obviously, it does have the summary of the equations and the tables and the charts and so on. So let me start by writing this is 1 and this is 3/7 2020, and this is the surveying workshop or review, whatever you like to call it. So the CVT, I hope that those who are either enrolled in the class or purchase the material from us, I hope the computer-based test is working fine for you. You plug it into the computer and the computer will generate 55 questions. And I hope this is helping you to prepare for the exam. Okay. So let me, it seems to me there is a question from one of you. You cannot hear me. Okay. I wonder if this from my end here, Faisal, anybody has a problem with the audio? Can you see my hand and the picture, or and also can you hear me? Okay, it seems to me everybody is hearing me. Audio okay, very visual okay. So it seems to me, Faisal, you do have a problem. So please get out and join me again. One of you is asking about collimation error. Everything is okay. Thank you very much. There is a handout. I send it, and normally we include this as part of our package. And this handout, let me show it to you. And the handout has the 2 big tests, and it does have application for the collimation error, as I'm going to discuss it right now. Let me bring the handout. If the handout is handy, if it's not, I will. Here it is. So this is the handout that's sent to everybody. It's a very thick package. I send it to everybody in addition to material, any material I found that it might help you to understand the subject. So I included. And if you don't have it, I would be glad to scan it and send it to you. So let us um, look to this handout. Um, it is in a thick package. It was sent to everybody. It's stable together. Very thick package. Okay. I hope that you have it. If not, as I said, I'll be glad to send it to you. Do you have a copy here with you? Do you have a copy? You don't have a copy of this? Okay. Okay, I will make a copy during the break and give it to you. No problem. So what is the two big test, or just simply the big test? As indicated in my book, that the two lines you don't have it either. Okay, if you purchase the material from us, or if you are taking the class, so you should have it. If you don't have it, I said I will be glad to send it to you. Okay, with the notes. When the notes are scanned and sent on Monday, I will ask my staff to include this handout as part of the discussion related to this issue. Okay. So bear with me until Monday. Somebody will scan the notes. Normally they scan the notes, the hand notes, and any attachment, and they scan it and send it to everybody, including you, even if you are not taking the class with us, and even if you are not having my books with you. So the two big tests, or the big test, PEG test. The purpose of the big test is to check that the line of sight through the level is horizontal, or basically it's parallel to the axis of the bubble tube. So if you look to any instrument like this, we have two lines. This, the whatever the instrument is. So you are looking through this eye. Here it is. This is our eye here. We look through the telescope. So this is the line of sight, where my line of sight will go through. So I'm looking to the instrument from this side, and this is the line of sight. This is the first line. The second line is the line of the instrument, or the bubble, okay, or the level bubble axis. This is a bubble here, okay, the vial or the bubble, okay, that one we use for three. There is left hand rule and right hand rule. We have a rule is called left hand rule. I discussed this in my book in chapter 3. I can show it to you. The left hand rule, where the bubble is moving in the direction of the left thumb. So normally we center this bubble to be in the center. This is for an instrument. It does have the three bubbles, okay, 1, 2, 3. So we need to make sure that the bubble, okay, it is in the middle. So we move it, the bubble, from right to left, or up or down, to make sure that the bubble in the center, exactly, to make sure that the instrument is level. So this is the first thing that we do after you put the instrument, the tripod, okay, supporting the instrument. Okay, you need to make sure that your instrument is level, 100%, because the ground is not level. So we play with these legs until you level the instrument to make sure that everything is leveled. So this line from the line of sight, and this line which is representing the level bubble axis, they supposed to parallel to each other, theoretically speaking. This is a perfect position, the perfect setup for the instrument. These two lines must be parallel to each other, But because we are dealing with instruments, and these instruments will be out of calibration from time to time, so we have to do this two big test, or the big test, from time to time, to ensure that these lines are parallel to each other. And this is what is mentioned at the beginning. Said that the purpose of the big test is to check that the line of sight, or the line through the level, is horizontal, which is parallel to the axis of the bubble tube. So this, I need you to know the purpose. Maybe you will be asked about that as a conceptual question, purpose of the big test. How we do that? How we perform that? In order to perform the big test, there are two setups. Setup number one, which is, they call it setup A here, setup number one, or he call it setup A. And the setup number two, or setup B as a boy. So what we do, we put the instrument, this is my instrument here, with the tripod, okay, in the middle between 2 points. Normally is about 200 feet. So 100 feet this side and 100 feet this side. Normally we drive a nail here, or a stake. And normally we base this. It's not exactly to be measured to the nearest inch or so. Normally we base it, mean that you walk and about 100 feet here and 100 feet here, or 30 meters here and 30 meters here. And you put the instrument in the middle, and you put the level, the rod, the surveying rod. You put the rod, you hold the rod, the surveying rod. So if these two lines are not perfectly parallel to each other, we're going to take a reading. It's called delta E1. He called it delta E1. Okay. And we take the same rod and put it at the other point, and we look to delta E1. Theoretically speaking, these two, they're supposed to be the same, because since the instrument in the middle, so the curvature and the refraction, as you know, we have something it's called C plus R, curvature and refraction. This is the curvature of the Earth. Curvature, sorry, let me correct myself very quick here, because so the curvature for C, because the Earth is not flat, the Earth, it has a curvature, okay, because it does have whatever radius is. So there is a curvature, and the R for refraction. These two errors should be used to adjust any reading, and this is why you will find in my book in chapter 5, you will find that there are 3 equations I provided in chapter 5 in my book due to C plus R. For those who have my book, it is equation 5-3, 5-4, and 5-5. C for curvature and R for refraction. So we need to adjust any reading that we take to account or to take into consideration the curvature and the refraction. And here are the equations that listed in the surveying books. Nobody will ask you to derive it. We can derive it, but nobody will ask you to derive any of these equations on the exam. So C plus R, if it is in meter, so this is the equation, C plus R, and the K, it is in kilometer. You have to be careful with units. Units are very critical here, units. Okay. And the second equation, C plus R, using the feet, this is the equation where the K is in mile. So the output will be in feet, but the distance will be given, the K distance in this equation with 0.574 K square will be in mile. And finally, C plus R in feet, curvature and refraction error in feet. This is on page, by the way, 118. If you have my textbook, page 118 textbook. Okay. And this is 0.0206 m square, where m in thousands of feet. So the they came up with these equations to account for the curvature of the Earth, and the refraction, the atmospheric refraction, which is basically the line of sight is not perfectly straight. The line of sight, they found that the line of sight, when it goes through different densities of air, this line of sight is deflected south, not south, down, yes, which is the south, down toward the Earth. If this is the Earth, and this is called the refraction. What is the refraction? Refraction is a deflection of the line of sight toward the gravity or toward the Earth because of the variation of the density of the air. So they found that. So the line is deflecting down. It's supposed to be straight. Okay. In order to, for the two big test, or the big test when we do it, in order to eliminate the C plus R, we're using a small distance. So this is 100 feet and this is 100 feet. So the curvature of this Earth is not really, it will be very small. Okay. So this is a setup number one. Setup number, we are taking a reading. This is he call it the error A1, and the error in 30 meters or 100 feet B1. So I have a reading here B1, and a reading here is A1. Remember these two readings because we need them on the back of the calculations. This is the first setup where the instrument is set up in between point A and point B, and it is in the middle. The setup number two, in order to ensure that these two lines are parallel to each other, because here very close to the instrument, even if they are not parallel, but in the vicinity of the instrument or close to the instrument, we can assume that they are parallel to each other. This is, you see here, it is the close here. So this is what we do. We move the instrument from here and put it here. You see, very close. So this is a surveying rod. And we put the instrument so close to the rod such that the person who is reading it from here, from this side, he will not be able to get the reading until somebody with a pencil and will go back and forth, up and down like this to indicate where is, because he will not be able to read until he see the pencil. In order that we do that, this is setup number two, where the instrument is moved against one of the rod, this one or this one. He moved it this way. Okay, so if we take a reading here, this reading is called A2. And you flip the instrument and put the rod while the instrument is still there. You flip the instrument and you take the same rod. It should be the same rod, by the way. Why we are using the same rod? Why we don't have two separate rods? One rod here and one rod here at the same time. Can we do that? The answer is no. Because we have something called instrumental error. Instrumental error. Let me write this down, at least you can. The errors in surveying, there are something we call types, and there are two types: random and systematic. So random errors and systematic errors. These are the types. Sources, there are three sources. One is called human error or personal, human or personal error. The second one is called environmental errors. Errors like magnetism and temperature and the humidity and magnetism and all these things. And the third one is called instrumental error. So when we are dealing with the instrumental error, when we are using equipment or instruments in general, we have to be careful because each instrument has its own error, okay? And this is why we do the calibration from time to time. So if you are using two separate rods, each rod, obviously, it has its own error. So we don't know exactly which one is more accurate than the others. This is why we're using only one rod. So one instrument, and one rod for all these setups and measurements to eliminate the instrumental errors, because whatever errors we have, it will be canceled out if you are using the same equipment and the same instrument. So putting the instrument here, and we are going to take a reading. It's called A2, which is almost over a distance of 0. The second reading after you flip the instrument, you are going to get another answer, which is B2, but this B2 over 60 meters or 100. So because we're assuming that the distance, the entire distance is still 200 feet or 60 meters. So after collecting A1, which is the error delta E1 and delta E1, they're supposed to be equal, because if the instrument in the middle and if there is an error on this side, when you take the instrument to the other, if these two lines, okay, they are not parallel to each other, so whatever error occurring over 100 feet on the left, it will have the same magnitude as occurring on the right. This is what we are assuming, okay? And after we move the instrument to be against the rod, so we get a reading is called A2, and after that we are going to get a reading, okay, this he call it delta E2. So we have delta E1 and delta E2. We have all these readings from these two setups. Here the explanation, they say that the line of axis is defined by the location of the horizontal crosshair and so all these things. So to perform the big test, the surveyor first placed two stakes at a distance of 200 to 300 feet apart. Here's the explanation, which is also, I have it in my textbook in chapter 5. In chapter 5 also I explained this, but I found this picture probably better than the picture I have. Here it is. And my book on page 120, but I use the term that most of the surveying books they are using, two big tests. If you go to page 120 of my textbook, you will find that the line of sight adjustment make the line of sight parallel, exactly the same thing, and the two setups also are shown here. Setup number 1 and setup number 2, and I explain the process as explained in the handout. But since some of you don't have my book, so I use this handout, and I found this handout probably it has a better illustration than the one I have in my textbook. If you flip the page, here's continue. The level is set up, okay, midway, which is based, as I told you, base it. We don't really measure to the nearest inch. Base it means that you walk it, okay, between the two stakes, okay, reading and then take the location, see figure so and so. If the line of sight's okay through not horizontal, the error is going to be delta E1, as we indicated here. If these two lines are not parallel to each other, so in this case there will be an error. Okay, theoretically speaking, it is supposed to be okay parallel to each other. So if you flip the page, this is a continuation, and here is talking about the collimation correction, and this is what you ask me. Okay, let's assume, which is, they call it the C factor. Okay, so you can read the rest here. This is exactly what I just talked about. But in order to translate this into English, let's go to the sample problem to illustrate that. Okay, let us, the first setup, here it is, the first setup. The reading A1 and B1. Let's assume that the reading A1 and the reading B1 are recorded like this. This is, theoretically speaking, is supposed to be what? It's supposed to be equal. Because as I told you, if the instrument is perfect, the error on this side should be equal, which we call it delta E1 and delta E1. But unfortunately, we got two different readings. So if you take the difference between them, and let me bring my calculator here to help me with that. If you take the difference between these two, you're supposed to get this number here, which is 1.075, 1.247 minus, which is correct. So this is the true difference in elevation between these two numbers. And after that, he took A2, which is this reading here, the A2, the reading, okay? And he gave you this number here. And the reading of B1, the reading of, is this B1 or B2? He put a footnote here. Had been and no error, the instrument of the line of sight, the rod reading at B2 would have to be 1955. Oh, okay, I know, okay. i.e., okay, it is the 1.783. He's saying that this is the difference. If there is no error, that means that this reading here is supposed to be 1.783 plus the difference, which is 0.172. So this number here, if you add it at the footnote here, it is 1.783 enter, and 0.172 plus is supposed to be 1.955. And when I scan it, I will scan it with these numbers. At least you know this is the footnote here, an asterisk here, and they said okay. So right now the difference between them, between this and this, okay, it is 1.783 enter, and the 1.946 minus, it give us 0.163. So this is the difference between this reading and this reading here. Okay. So right now, the error delta E2 right now, delta E2, okay, this error here in 60 meter, okay. If you take this number here, 0.163, and you divide it by 60, no, wait a second. This is, he is using meter or feet. So 0.163 enter. Oh, the error, okay. The error is equal 0.009. How he got 0.009? Now I know, okay. The 0.172, this is the 1.172 from the setup number 1 and 0.163. So 0.172, let me make sure that this is 0.163 minus, bingo, yeah, this is the number. 0.0, this is minus, so it is equal 0.009, which is a difference between, from setup number 1, this is setup number 1, the difference, and setup number 2, the difference is 0.009. Okay, this is in 60 meters. So if you take this and you divide it by 60, so 0.009, this is meter over 60. 60 meter is the total distance he's using, okay? So this will give you this error here, which is the 0.0015. So it is 0.0015, which is basically the error divided by the distance, 60 meter. So this is what is called the error of collimation, okay, or the collimation, okay, correction, or the collimation error, as we call it. Okay, so this is the way we do it. Okay, as far, and when you receive this, please read it, and I would be glad to go over it again one more time if it's not totally convincing. Okay, so and also in the blue book, I don't know, I think they have it in the blue book, the surveying, definitions of surveying and the associated terms. Let me see if this ABC, it should be there. I think I remember I saw it. So the collimation, okay. I'm still looking, just let me see. I think COLL. Okay, I'm getting close. Yeah, it's very important to have this book with you, the compensating consideration, or a lot of. Yeah, it is written here. It is a collimation error. Okay, collimation error, here it is. So this book, I highly recommend you to take it with you just in case if there is one definition. Okay, collimation, the purpose of bringing, okay, the optical element, okay, of an optical system into proper relationship with each other. The process of bringing the collimation system into proper relationship with the pointing, the mechanism is called, okay, alignment, is using the word, okay, adjusting and so on. And the collimation error is the angle, okay, between the line of collimation, which is the line of sight, okay, of a telescope and its collimation axis, which is, we take the error divided by the distance, will give us, which is given in this assembly. So I highly recommend you to read this definition and read it, okay, and when you receive this, go over it, and I will be glad to discuss it again if it's not clear to you, or if it's not very clear. Let me put it that way, okay? So this will be scanned and sent to you on Monday. And try to do your best to remember the difference between the types of errors and the sources of errors. This is something very, very important that you might ask, or they might see something like this on the exam. Okay, let me move to the second question. If there is any second question here, you are very welcome. Okay, and as I said, that you will receive it with the Kaylee. Okay, you are going to receive it with the handout on Monday. Okay, and read it carefully, and I will be glad to go over it again one more time. I don't know when you are taking the exam, but let us do our best. Okay. I received. Okay. For the horizontal curves, horizontal circular curves. In my book, in chapter 10, if I remember, I discussed the reversing curves. Yes, in my book on page 240, after we discussed the compound curves, and compound curves, by the way, they are also important. I'm not saying that, and we need to make sure that you really understand how to deal with it, because they are lengthy and they have equations that very similar to a simple curve. So the compound circular curves, excuse me, compound circular curves, basically two curves are connected together at a point we call it PCC, which is a point of compound curvature. I need you to remember that the equations for compound curves are identical or similar to the simple curve, except one equation, which is the overall delta. The overall delta, okay, it does have the sum of the delta 1 and delta 2, because we have two deltas. This is a delta 2 for circular curve number 1, and this one here is delta 1. because basically two curves, each curve has its own radius, and they are connected together at a point called PCC, which is a point of compound curve, a point of compound curve or curvature. BCC, point of compound curve or the point of compound curvature, whatever your preference is. And the delta, which is external angle delta, I needed to remember is equal delta 1 plus delta 2. This is a very good equation we need to pay attention to, because without knowing this relationship, you will not be able to solve the compound curves, which is delta is equal delta 1 plus delta 2. This is delta 1 and this is delta 2, by the way. Here, this one here is delta 2, also, which is the deflection angle. Okay. The reason I'm mentioning that, because there are another set of equations, which is the distance from here, from the vertex. Okay, this is the vertex, or PI. PI is the most common name instead of the vertex. Vertex we use for vertical curves, but for horizontal curves, normally we use the PI, which is a point of intersection. The vertex is very rare. Let me take it out because very few books. So this point here is a PI, which is a point of intersection. So the distance from here to here, which is the distance from the beginning of the curve, okay, to the overall PI, okay, and the distance from here to here also, I have it in my transportation books right now in form of equations, and they are very important, by the way. Transportation and also the civil breadth AM. I would be glad to send it to you, because they might ask you. They might. Let me see it to see if I think I saw it today when I was talking about something today. Here it is. This is a compound curve, a compound curvature, or compound curve, compound circular curves. Basically, there are two curves. They are connected together at this PCC, the one we talked about. So this is a curve, and the second curve, I would be glad to send this picture also. And this is a common tangent, and I'm talking about this here, the T sub A and the T sub B, which is the distance from the PI to the beginning of the curve and BI to the end of the curve here. These two equations, they are given by these two equations. T sub A and T sub B, equation 27 and 28. And I remember very well that these two equations for the TA and TB, they are only given in one book for some reason, and for the PE exam, they start to use these equations lately, and they reference this book. And this book, I used it when I was teaching surveying work way back in Las Cruces in New Mexico. Sorry, the allergies start to bother me. Something is called Route, Location, and Design. This is a very old book by Hickerson. Probably I told you about it before, but it still is a very good book. Even it was published way back in 1926, and the last printing 1964. I don't know if you can find it or not in the market. And they still, until now, the NCEES, they are referring to this book as one of the references for a transportation. And specifically, they asking about this T sub A and T sub B. So I'll be glad to scan this and send it to you just in case if they ask you. Okay, another thing that also I need you to be aware of, which is the reverse curves. And let me write this down, because reverse curves also, they are important. So horizontal circular curves, either it could be simple curve, okay, which is a similar arc where we have the central angle delta and r, and the beginning of the curve, the end of the curve, and all the equations that you are familiar with, or if you want me to go over one of them, I would be glad to do that. Simple curve, or it could be compound, where we have two curves are connected together at a common point, which we'll call it the BCC. So this curve here, followed by another curve, probably shorter one. Here it is. And this is, so this is R2, and this is R1, and this is delta 1, and this is delta 2, and each curve has its own center. It could be O1 here and O2 here. And this is a point that we call it PCC, where a common tangent, a tangent to both curves will be here. And after that, if you have the back tangent, this is the beginning of the curve, or PC. So extend this like that. This will form PI1. And if you look to the other tangent, with at the end of the curve here, and you extend it like this, it will intersect here at PI2. PI2, which is the point of intersection for curve number 2. Okay? And if you extend these two tangents, the back and the forward, they are going to intersect at the common PI, which is this one here. Let me use different color. Here it is, and extend this to this. It will intersect here. This is a PI. Okay, so the compound curves, excuse me, the allergies start to work a little bit this afternoon. I don't know what happened, but I will try to do my best here. So the third type of horizontal curves I needed to be aware of, which is the reverse. Reverse. The reverse curves, we have a curve in one direction, right curve to the right, followed by another curve to the left. Okay, we could have a tangent here, and tangent could be parallel or not parallel. I consider both of them in my book. Okay, like this one here. Let me show it to you in my textbook when we're talking about. Here it is. This is on page 241 for those who has a book. On page 241, and I will tell you why I'm talking about this right now, because I need to add another two equations just in case. So reverse curves, we use it a lot. For example, this is a back tangent, and this is a curve to the right. By the way, this curve here is curve to the right. Curve to the right. Why we call it curve to the right? Because with respect to the beginning of the curve, if the curve is turning, this is on page 241 of the textbook. And this curve here is curve to the left, by the way. This is curve to the left. To the left or to the right, as I told you, with respect to the beginning of the curve. So if this is the tangent, if the curve is turning this way, if this is a PC or the beginning of the curve, if the curve is turning toward this, this is to the right. If the curve is turning on the other direction, they agreed to call this to the left. To the left. Left, here it is, left. And normally on the exam, they didn't tell you which direction, because the answer does not make any difference if you draw it to the right or to the left. But if the answer or the answers will be affected by the direction of the curve, he has to tell you is the curve with respect to the beginning of the curve is to the right or to the left. So if you are here right now, if the curve is turned to your right, you are standing here. So this is curve to the right. If the curve is turning to the left, this is to the left. Okay, so just to let you know. If they don't say anything about the direction of the curve, that means that it does not make any difference, right or left. Normally, right and left will be affecting the coordinates. If you have a question and the question asking you to determine coordinates, in this case, the direction of the curve is the critical. It must be stated in the problem which direction he is talking about. So going back to the reverse curves could be having the two tangent parallel like this, or non-parallel tangents, which is about the back tangent and the forward tangent. It depends on the geometrics and depends on the constraints. But if you have this scenario here, parallel tangents, I need you to be aware of the following. There is a distance which we will call it the offset distance. Offset. What is the offset distance? The offset distance is the distance between the back and forward tangent, but it is a perpendicular distance, this one here. It's called offset. Well, this is a perpendicular distance between the back tangent and the forward tangent. This distance from here, perpendicular distance between these two. And this offset is given by one equation. I need to add it. Okay, it is R1 plus R2. This is R1 and this is R2 time the cosine 1 minus cosine delta. 1 minus cosine delta. And normally delta 1 and delta 2 are equal in this case if they are parallel, by the way. So let me write the equation again. It is R1 plus R2, close the bracket, times 1 minus cosine delta. This is equation that I needed to be aware of just in case, because I believe I saw a problem somewhere. Somebody asked me about it, and I told them the equation. We can derive it, this equation, but nobody will ask you to derive, as I always say that. Yes, sir. So, no. Yeah, I think. No, delta 1 and delta 2 will be equal in this case. So either one of them. So this is either delta 1 and delta 2 are equal in this case. Okay. So either one. No, this is not the compound curve is a delta 1 plus delta 2 is equal delta. No. For reverse curve, no. So we are assuming here delta 1 and delta 2 are equal. So either one of them will do the job. You are very welcome. The other one, the other equation I need to add related to reverse curve. So this is the offset. They call it the offset, which is how much the distance from the beginning here to the end of the curve. From the beginning of the curve to the end of the curve. And let me use different color here. And I write the equation for you, which is from here to here, the horizontal distance between the beginning of the curve to the end of the curve. This distance from here to here is R1 plus R2 times the sine delta. And in this case, we are assuming that delta 1 and delta 2 are equal for this situation. Because this line is parallel to this line. This line is parallel to this line, and this line is crossing it. So this angle and this angle, they are opposite to each other, and opposite angles must be equal in this case, okay? Because this is perpendicular and this is perpendicular here. So these two equations, I need you to remember them, that this is the R1 plus R2 sine delta is the horizontal distance between the beginning of the curve to the end of the curve. So I will write it here. This is the horizontal distance from the beginning of the curve to the end of the curve. And I will be glad to prepare some problems next time. Somebody sent me a problem. I told you, yeah, it's very easy, but I need to okay. So so this is for the horizontal and for compound and reverse curves. Okay. Even I can, or let me wait until I get the problem for you. Will be much better. I don't like you to. So the problem about somebody asked me why I did not provide drawings. Yes, this is another question that came up from one of you. In the chapter 10, I will go over this before some of you, they are raising the hand. Let me answer the questions first before I move on, because probably maybe they are related to what I'm talking about. I had a question, Larry, question. Okay, I'm sorry. Go ahead, Larry. Okay, let me see, Larry. Where is Larry? Here we go. Go ahead, Larry. You are on the air.
Hey, how you doing, Dr. Mansour? How are you?
Thank you very much. Yes. What's up?
Okay, going back to the reverse curve.
Yes.
I do remember seeing a problem on the test, very similar, but I don't think they gave you the delta. But they wanted you to solve for the horizontal distance. There's got to be a way. Is there? I mean, they might have given you maybe the radiuses, but that's it. You couldn't. You had to figure out how to get the delta in order to solve for the horizontal distance, right?
Let me translate your question into something and correct me if I am wrong. This is most likely it is parallel tangents, because non-parallel tangents will be based on what you're describing to me is not applicable. So let's assume that they are parallel tangents. So the first curve, let me draw something and correct me or say that this is a curve. Okay. Whatever on the exam, it does not make any difference as long as we understand the concept. And this is another reverse curve, another curve in the opposite direction. Okay. And this is a second tangent, or the forward tangent. So this is called back tangent. This is the beginning of the curve, or BC, and this is the end of the curve, or PT, point of tangency. And this curve here, okay, okay, try to draw as much as I can here. This is R1, and this is R2, and since these are parallel, so delta 1 and delta 2 in this case geometrically must be equal. So let us assume, for the sake of discussion, that I gave you something like this, and I'm telling you from here to here, the offset distance from here to here is 20 feet. Okay? Assuming that. And I'm asking how far from here to here, which is a horizontal distance. So this here, I will call it distance D, or horizontal distance, horizontal distance between the beginning of the curve and the end of the curve, assuming that the R1 and the R2 are given. Let's assume they are equal. R1 equals R2 equals 2,000 or 5,000 feet. Is this something you can handle? Is this something that we can handle? The answer is yes. Okay, so can you calculate the distance? Let me give you 3 minutes to calculate this horizontal distance. Okay, so this here, the 20 feet, this is called the offset. The one I gave you the equation offset. Okay, and the offset is given by the equation, as I told you, that it is R1. So the offset equation, this one here, it is R1 plus R2 times 1 minus cosine delta. 1 minus cosine delta. So in this case, let me move it away from this crowded area here. At least you can follow it or read it. So this offset, which is 20 feet, is given by this equation, which is R1 plus R2 times 1 minus cosine delta. So this is the offset, which is the 20 feet. After getting we can solve for delta from here, because the offset is given, and R1 and R2 are given to be 5,000, make it easy for us. He's asking for the horizontal distance, this here. And the horizontal distance is given as R1 plus R2 sine delta. So I will get the delta from this step, and I will go to the second step to get the horizontal distance between the beginning of the curve and the end of the curve. And in this case, the problem is fully solved. So I don't know which one or which were given, or which items or which numbers were given and which number were not given, but go ahead and solve this problem, and I will be glad to, as I told you, I can prepare more problems related to it, but assuming that this is a problem that's given to you. Can you tell me what is the offset, the horizontal distance, knowing the offset? I will give you 3 minutes from now. Okay, exactly as the exam. Let me give you 3 minutes. I will put you on mute right now, my friend, until you solve it. And after that, we will discuss it to see who got the right answer, and we'll take it from there. Okay, I will put everybody in mute. So let us look to this problem here, the one I just made it up for the reversing curve. And so if the offset is given to be 20 feet, for example, and the R1 and R2 are given 5,000, 3,000, whatever it is, and what is this horizontal distance from here to here? Okay, and I will talk about this after. So problem number 2 here. So if 20 feet, which is offset, is equal R1 plus R2 times 1 minus cosine delta. So in this case, the 20 over R1 plus R2 is equal 1 minus cosine delta. So I can solve for delta as equal inverse cosine. I will get this way and get this way. It is 1 minus 20 over R1 plus R2. So in this case, delta is equal inverse cosine of 1 minus 20 divided by 5,000 plus 5,000. Okay. So the angle delta, according to my, let me calculate it and let me know if you got the same number or not. It is 20 enter over 10,000, a small number, and you subtract this 1 minus, and you take the inverse cosine. Okay, and we need to make sure that we are setting up your calculator to the right mode. So it is 20 enter 10,000 divided. Make sure that I did this correctly. And this is 1 minus, and inverse cosine, because the angle came very small, which is a little bit. I get an angle delta of 3.624 degrees. I don't know if you got the same answer or not. And in this case, R1 plus R2 times sine delta. Okay, this will give you the horizontal distance. The horizontal distance. So R1 plus R2, 5,000 plus 5,000 times sine this angle, sine 3 degrees and 624 degrees. So this will give me a very small number. So it is 3.62624 sine, and you multiply this by 10,000 times, it's about 632 feet 09. So this is the answer I got. And this is, we can just elaborate on this. I don't know if anybody got the same answer I got or not. If you are getting the same answer, that's good news. Still, if you didn't get the same answers, that's still good news. At least you can correct me or I will correct you, whoever is. Okay, yes, I got, okay, so 632.14, that rounding, it depends on how many decimal places did you carry, my friend, is good enough. Okay, the equation I just wrote, okay, which is, if you look to the first curve, okay, let's assume that this is R1 and this is delta, or let me make it the general case. I don't like to have a special case, because a special case is going to be, you are telling me that this special case, and just to show you that how the equations are related to each other, very quick, just in case. So this is the back tangent, and this is BC, or the beginning of the curve, and this is delta 1. If you look to this, and we are talking about the R sine delta 1. If you look to this, draw a line passing through this point here. This is R, still R1, and this is 90 degrees. So if you look to this distance from here to here, I will call it H, and I will call this is V. And this is 90 degrees. So, and this is delta. So H over V, over R, sorry, over R1, the H over R1 is going to give you the sine of delta 1. If you look to the second, this is, let me call it H1. And if you look to the second curve, which is the reverse curve, and this is delta 2, and this is R2. Again, if you continue this like this, horizontal line, like this, and I will call this is H2 from here to here. Again, H2, and this is still R2 here, because this is O2. So H2 over R2 is still equal sine delta 2. So in this case, we are saying that the H2 is equal R2 sine delta 2. And from here, we can say that the H1 is equal R sine delta 1. But the horizontal distance from the beginning of the curve to the end of the curve, the horizontal distance is equal what? Is equal to H1 plus H2. So if you put H1 as R1 sine delta 1, and you put H2 R2 sine delta 2, okay? So if in our case delta 1 equals delta 2, so in this case you can say that this is R1 plus R2, factor it out, and sine delta 1 and sine delta 2 will be taken out, and this will be sine delta, and this is the horizontal distance that I gave it to you here, just in case if you are try to visualize what's going on. By drawing, come here, and this is the BRC, the point of reversing curve. This is the PRC. Okay, so you have a curve to the right and curve to the left, and as you can see here, this is a curve to the right, and this is a curve to the left. Like that. As far as the offset, by the way, the offset, which is a vertical distance, okay, the vertical distance. So this distance here, is, and this distance from here to here, this distance here is equal R1 or R2 in this case, minus this distance here. This distance here, you can get it in terms of this as a cosine. And the same story, this distance here. So if you take this distance and this distance, this will give you the offset, which is the equation, the second equation. I don't need to derive it, okay? But just in case, offset, okay, is equal the R1 plus R2 times 1 minus cosine delta 1 minus cosine delta. And I need to be familiar with these two equations. So I hope Larry, I hope that Larry, this discussion here it did help you. If it didn't help you, please let me know or email me exactly what is missing on the reverse curves, and I will be glad to come up with. Uh, I have many problems, but I need to locate them first, and after that. But I need, when you receive this, please look at it, and if you found there is any typo or mistake or an error, please let me know, and I would be glad to correct that or to elaborate on it in our next meeting. Okay. So this is something I needed to be aware of. Okay, I got it. Okay, good. I'm glad that you got it. Okay. Let's take a few minutes break and come back, and we'll continue our discussion. Give me a few minutes. Okay, it is right now 5:50, so 6 o'clock we are going to meet again. Thank you. Okay, welcome back, everybody. Let's continue our discussion here. And one of you is raising the hand. Let me see who is. Okay, Larry. Okay. Yes, Larry, go ahead, please. You are in the air.
Yeah, Dr. Mansour, I was wondering if you could go over the certain problems. I know there's not much time today. Can I give you a couple of problems or?
How we are going to give it to me?
Well, I think the problems that I'm having biggest questions are on problem 204.
Oh, in the textbook. Okay, I have number. I thought that.
CBT 497.
Okay. Which problem is that?
Problem number two. Okay, I'm sorry. Problem number 203, I believe.
Okay.
That's one problem. And then the other one, so problem 203, and
Okay.
the next one would be problem 224.
224.
203, 224.
Let me just circle them.
The 497 CBT.
224 and what else?
I would say 248
Okay.
would be the third one. That's it. I don't want to, I know there's other students who have other questions.
So it is 203. Let me just mark them. At least I will not forget them. 203. And 224. And what is the third one, Larry?
Yeah, 248.
248. Okay. So let's start from the back here. From the last, but let me put you on mute again. At least you can have the freedom to, and it will not make any. So problem 248. Let me read the problem that also about the big test. And they are asking for the big adjustment test shows that the level line of sight is inclined toward, okay, 0 per 100 feet. What is the allowable difference between the backside and the foresight distances, okay, at each setup, neglecting the curvature and the refract? Do you remember C plus R? They showed up here again. In order to keep the elevation correct within 0.0001. So, okay, so we have a two big test. Okay, show that the line of sight is inclined the line of sight is inclined instead of horizontal, inclined a distance of 0.0045 in over 100 feet. Okay, so it is 0.0045. The error here, or the inclination over 100 feet, I need to proportion this. I need to keep elevation correct within this. So this is feet also, as 0.001 feet over a certain distance d. So if you look to this, I set up, so I proportion the error to the distance to the correction that, or to be within this amount in reference to a distance which I don't know. So I can solve for the distance as 100 feet times 0.001 feet divided by 0.45. So if we do this piece of calculation, we'll see what answer we're going to get, and if there is any answer here to match this. So it is 100, enter, 0.001 times, and 0.0045 divided, I get 22.22 feet. Okay, so do I have an answer to match that? 21, 22, 22, 2, and 25. And the best answer I will pick the answer B as in boy. I don't know if this is a correct answer or not. You can check the answer on the back of the book to see if this is correct or not, um, Larry. And so basically, the big test, as I told you, that when we getting the error over a distance, okay, in this case we can use this proportion in order to ensure that we are getting whatever reading to keep elevations within 0.00 feet. So it's saying that what is the allowable difference between the back side and the foresight distances at each setup, okay? Because right now when we are setting the instrument like that, so this, as you know, from here to here, if this is a benchmark, so we'll call this is the back side, sorry, which is a point of non-elevation, and we go to the other side. This is a foresight FS. So they is saying that these distances here, what it should be, what is the allowable difference between the backside and the far side at each setup, okay, in order to keep the elevation correct within whatever he gave you. So I proportion the error that we are getting over 100 feet is equal to the accuracy over the distance, and I solve for the distance. Makes sense? Okay, so this is the problem that you are talking about. The second problem, problem number 224. 224. And you are very welcome to stop me if problem number 224. It is required to lay out a rectangular commercial building 60 by 100 feet. So I have a 60 by 100 feet. This is a building. I need to lay it out in the field. And the question is very layout. It's a keyword. Every question, by the way, has a keyword or keywords, keyword to lay out. If the steel tape is being used, actually the tape is 100 feet, but actually it is 100.04 feet long. So the tape is too long. Okay, and in chapter 4 of my book, let me show you a table I provided to you, and this will help you a lot. The difference between layout and measurement. I came up with this table because this table is given on page 93. Page 93 of the textbook. If we understand this table is going to help us a lot, and without any confusion during the exam, because during the exam, as I told you, the biggest enemy for you is time. So this is the table that I highly recommend you to use it. If the tape is too long, when you have a measurement, you add the error. But if you are laying out a distance, you subtract the error. There is a huge difference between to lay out or to correct a measurement. Okay. And if the tape is too short, the signs will be opposite. Let me put this aside and explain to you the difference between them. And you have no time during the exam to think. The time during the exam should be used only for solving problems quickly and accurately. Measurements. Either past tense, something happened in the past, or future. In future, we use the word layout. To lay out. Past tense, measurements has been recorded. Measurements have been recorded. Past tense. For example, you give me a tape, the tape that we are talking about here, it is. The tape is supposed to be reading 100 feet. This is theoretical. But the tape was manufactured wrong. And the actual tape length is 104 feet. The tape was, this is actual. So theoretical 100, but this is actual. Actual tape length. So is the tape too short or too long? The tape is too long. Because longer than 100 feet. It has 400 of a foot extra. Because it was manufactured wrong or whatever reason is. So if this tape is used in these two cases, the past tense and the future. If you send me out, Mr. Mansour or Dr. Mansour, take this tape and measure the distance from A to B outside. And I came using this tape. I told you the distance from here to here, I found it to be 500 feet. Remember, the tape is marked like this. The tape, it has 0, it has a 100-foot mark here. It doesn't have 100.04, no, but the tape is longer because what's manufactured wrong, but still the number showing on the tape to be 100 feet. This a distance that measured, past tense, measured. what is the true distance between A and B? This is measured, and I need the true distance between A and B. Can you tell me what is the true distance? Because this is not true, because I use a tape that it does have 100-foot mark here, but actually is 104. So is this true distance is 500 feet or less or more? Huh? Give me the true distance. I'm asking a question, and do it and tell me what is the true distance. I'm waiting for an answer. Okay. So what is the true distance? It is less than 500 or equals 500 or greater than 500. Huh? Greater. And what is the true distance in this case? 500.2 feet. Because I use the tape measuring the distance from A to B 5 times. Every time I do have an error of 0.04. I am reading 100, but actually is 100.04. So the actual distance between these two is 500. So the error here, did I add the error or did I subtract the error? I did add it. And this is what is shown in my book on page 93. When the tape is too long and you have a measurement, so the error must be added. Here it is a plus. So the error must be added because the tape is too long. Do you understand me? Okay. Right now, go to the other extreme. You ask me, Mr. Mansour or Dr. Mansour, I need you to take this tape, which is 104.04, and I need you to lay out. Here it is. I need to lay out 500 feet. I put a nail here, and I need to use this tape to lay out a distance to be 100 feet exact. How much I need to lay out in the field? I need a distance to be 500 feet actual. This is layout 500 feet. This is the actual distance or the true distance. Using this tape, the tape is too long. How much I need to lay out? (499.8 feet). I need to lay out this distance. Because again, I have 5 measurements. Every measurement, it has an extra distance. And this is why you look to my table here. When we lay out, we subtract the error. So you need to pay attention to this table. This table is so powerful. Table 4-4 of the textbook on page 93. If we understand this table, it could save a lot of time, and obviously, hopefully that will help you to get the right answer. Let us go to the problem that our friend is asking. Problem 224 of my book, the 497 CBT. Can you answer it now after this? This is layout or measurement. You are required to lay out. This is a future. Layout. And the tape, I'm still using the tape that is extra 0.004 in it. So what is the answer? Because when I use the tape, this 100 here, I will use it, I will lay out 99.96 feet. And this is the only answer, by the way, for this side. The other side, which is 60, okay, I need to lay out what? I need to lay 60 feet minus, I am using only 0.6, and I have 0.004 in each measurement, 0.04. So this will give you 60 minus 6 times 24, which is 0.24. Is this correct? 60 minus 0.6 times 0.4 is what? 0.0, okay, yeah, it says 24, but I have 2 zeros right now. So 0.04 enter 0.6 times is 0.024. So here it is, 0.024. I'm missing a zero here. So 0.024 from 60 minus, so this will give you, it is 59.976 or 59.98 feet. This is what the rounding, which is this number here. Okay, why did I multiply 0.6? Because this is 60 feet. For every 100 foot, I do have an error 0.04. So if I use only 60% of this table of this, how much error? And here it is. So the answer B is, but by getting one side only, you can select the proper answer. And we are lucky that he has, maybe if this is 99.96, that means that the answer between here and here, assuming that, okay, and he might give you another number here. But we are lucky that we have only one answer that matches the long side. In this case, automatically the other dimension is correct. And so I needed to remember the concept I just mentioned, which is if the tape is too long or too short, which is shown on this table here. Excuse me again. It is okay. If the tape is too short, I told you this will be the opposite. This will be negative and this will be positive. Please look to this table, and if you have any further questions, please let me know. Okay. And the last problem that our friend is asking about, which is a problem 203. Problem 203. Okay. Let me just make sure that everybody is on the same page with me, or probably they have some questions related to the two problems I just talked about, just to make sure that we are on the same page. Where is the 0.6 coming from? Oh, here it is. I hope that you got it clearly. The 0.6, which is 60 feet, because I proportion the error. Here it is. Your question, I hope that I addressed it. I answered, but I will repeat it again. The 0.6, the 0.6 coming from what? This 60 feet, and this is 100. So for every 100 foot, I do have an extra 0.04. So if I have 60 only, so I proportion 60 means that's 0.6 compared to 100. Okay. So if it is 60, how much is the error? If I have 100 feet, I have an error of 0.04. This is how we wrote the equation. So how much is the error? Is 60 times 0.04 divided by 100. You can write it this way as 0.6 times 0.04. I just proportion, here it is. This is another way of write it down, but I did it in one step. That's fine. Here it is. So I'm proportioning. If 100 foot has an error of 0.04, what about the 60 feet? How much error? Here it is. So I subtract this from the 60 feet, and this we ended with 59.98. I hope this is clear to everybody. Make sense? Good. Going back to the problem that you are referring to, which is a problem 203. 203. Normally, or always, I recommend always draw a sketch. Draw a sketch or a diagram or anything to illustrate to you or to explain to you what is meant by this problem. And the more you draw, the better the chance for you to understand the problem on the exam. Okay? So let me give you a couple minutes to try to come up with a drawing. If you can come up with a drawing or illustration, will be very good in order to a problem 2 or 3, please. Try to draw it and see if you come up with a drawing. Okay, a slope distance of 165 was measured between 2 points whose elevations were 447 and 448. So I have 2 points, point A and point B, for example. The slope distance, which is the distance along this slope here, between these 2 points was found to be 165.36 meter. The elevation, whose elevations were this elevation of point A, it does elevation 447 0.401, and the elevation of point B is lower elevation, so 445.389. So far, so good. We need to agree on the step by step. Point B has a lower elevation, or point A has higher elevation. He said that above the datum, whatever the datum is, the height of an EDM and reflector are given to be like this. Okay. We have an EDM. If we put an EDM at this point here, electronic distance measuring device, EDM, so the height of the instrument is 1.47 meter, and we are putting a prism or reflector here, a prism, which is, it will take the waves, and the instrument, let me put it that way, I can tilt it this way, I have no problem, where the instrument will send the, so if this height is given, and this height is given, so this is the height of the reflector, which is 1.615 meter, and this here is 1.47 meter, the HI from here to here. The horizontal length of the line AB, I need to get the horizontal distance. And I know some drawings are really difficult to visualize, okay, or to imagine. Let me draw it on my drawing a little bit. Okay, remember the wording, by the way, the future and the past tense. A measurement has been taken, or measurements have been recorded, and this one, okay. So I'm saying that, let me draw it a little bit. Okay, so this is the OG, and we do have a point A. Let me get my camera here ready for you. A point A is here, point A, and the point A has an elevation of 447.40, and there is another point here, he called it point B, as in boy, and the elevation of this point B is given to be 445.389, and this is 401, by the way, 389, 3 decimal places here. So this is a higher elevation, this one. I said that if we put the instrument here, and the instrument, let's assume it's tilted that way, the EDM, and he said that the HI, which is the height of the instrument, is given to be this distance here is 1.417 meter, and the prism, okay, as you know, the EDM, what is the EDM? The electronic distance measuring device. It does have source of waves. It will go to the reflector or the prism. This is the prism, okay, and the waves will come back. Based on the wavelength, the EDM will be capable of calculating the distance from here to here, the horizontal distance. Now this is EDM, they work on based on the waves, okay, the wave frequency and the wavelength and so on. So I do have a prism here, where and the slope distance, by the way, I should mention that slope distance is 165.360 meter between these 2 points. And the HI here is, or the HN is for the prism is given to be 1.615 meter. And he's asking what is the horizontal distance? What is the horizontal distance between A and B? Let me get a straight edge here. Try to draw it. At least you can, when you receive my notes, you will be able to read it. Okay. The horizontal distance is from here to here, or from here to here, whatever it is you would like to call it. This is the horizontal distance between point A and point B. Or if you'd like to measure it from the bottom, I have no problem with that, still the same. Okay, so here it is, from here to here. This is the horizontal distance h. I know the slope distance from here to here, which is the same as this from here to here. So this is 165.360. How much the difference from here to here? I will take the elevation, the 447.401. I will add the HI, which is 1.417. I will add that. So this plus this will give me here. And the elevation here plus this will give me here. So minus the 445.389 plus the 1615 and point here. So if you add these two numbers and add these two numbers and take the difference between them, this will give you this vertical distance from here to here. Do you agree with me? So the vertical distance V, which let me do it very quick to see if it is 447, which is the elevation of point A, 447.401, enter. And you add the height of the instrument, which is 1.417 plus, and you subtract these two, which is 445.389 minus and 1.615 minus, I get 1.8. I hope that everybody is reviewing my numbers. 1.8 something. 1.814. This is what I got. So this vertical distance is 1.814 feet, which is this distance from here to here. Okay. Since I know the vertical and I know the slope distance, can I get the h? H is equal, Pythagorean theorem is 165.360 square minus the number I just found, 1.814 square. So, and take the square root. So it is second square and 165.360 second square minus, and take the square root. I get 165 point almost 35 feet. Do we have an answer to match this? Let me see what are the answers given. 1.165. This is my answer here if my math is correct. Did you get the same number, sir? Okay. So here it is 165. Oh, they are very close. Oh my God. So I will pick B. There is no room here for error. I don't know. I hope that they will not give you. Okay. I remember when I made these problems, sometimes I made it so difficult. But yes.
We just use the elevation difference to figure out the height and find out horizontal.
One more time. Here is the HI. This is the HI 1.417.
Yeah, they are pretty low.
Okay.
Elevation.
You can, because yes, what you would like to eliminate the addition. I add this to this, and I add this to this, and I took the difference. You are telling me that these are close, but if you take the difference, I think you will not get the answer. Did you get the same answer, or getting very close?
Pretty close.
Very close. You took the you took a straight difference between 447. Okay, because probably the Pythagorean 447.401 and 445.389 minus, okay, and you said that this is square root, or sorry, square it, and 165.36 second square, and subtract, and this, and take the square root, still, okay, very close, 0.34775. So it's, but this is the right way. This is a more, no doubt about it, because we are lucky that probably these two numbers are not close to each other in this case. So we need to do it the right way. But you would like to save one extra step, or one, I have no problem with that. Any time you can save, since they are close to each other, you can say that and do it. No problem. I have no objection to that. Okay, so I hope these problems, Larry, are clear to you right now, or clear to everybody in the class here. And 1, 2, 3. Okay. I don't know how many of you are taking the exam very soon, but I wish you the best. If for those of you who are taking the exam very soon, and for those who are going to take the exam later on in the second quarter. I wish the best to all of you. Any other questions or problems you want me to elaborate or explain, or concept, or 1, 2, 3, and I will include this, which is a double-sided. You will get it. Okay. But for some reason, the allergy is bothering me too much this afternoon. Yes, sir. Yes, I have. Go ahead. Okay. Let me see who is here. Yes, Larry, go ahead. What other questions you have? Okay. Faisal, on March 21st, I wish you the best, Faisal. If you have any question, please let me know. Let Larry to see what other questions he has. Okay, Larry, I don't see. I'm trying to read your questions, or unmuted you. Let me unmute you. At least you can speak out. Yes, go ahead, Larry. You're in the air.
Hey, how you doing, Dr. Mansour? I'm going through my CBT 497.
Okay.
I'm looking at maybe a couple of conceptual questions.
What are these questions?
423 and 424.
So let me write it down. 423 and 424.
Correct.
Okay.
Yeah.
Okay. Let me look to these problems. Hopefully I can help you. Okay. 423. Let's go to 423. This is at the end. Okay. 423 and 424. These two questions, I will answer them for sure. Try to help you. This is in relation to chapter 14 of my book, of the textbook. The chapter 14 is talking about USPLS, United States Public Land Surveys. Okay. As I said that lately on the exam, based on the exam format, even I left this chapter. I don't like to take it out. I left this chapter because I felt that maybe uh, uh, one question indirectly related to this chapter, chapter 14, even in the description of the exam specifications, is not directly clear about or is directly indicating that the USPLS, which is the Division of Public Land and Township and sections, standard section, non-standard sections, all these things. So I always say that try to do your best to cover this chapter, chapter 14, read it once or twice, and that's it. And I will be glad to answer any question. But there are two corners. One is called the standard corner, and one is called the closing corner. When they divide the land during President Thomas Jefferson, when they divided the land, they have what is called SC and CC. SC is a standard corner, as from its name, a standard corner, and the other one, which is a closing corner. There is a map showing in chapter 14. I will take you to the map. Probably the drawing is much better. If you look to the how they divide the land, and we're talking about California, for example. So we have what is known as the IB, initial point, and this is called a baseline. And this is a standard meridian. The y-axis is called the standard meridian. Okay. When they start to divide the land, they start from the baseline and they have townships. Each township is 6 miles. Okay. So 6 miles. And the lines start to go up as we go to the north, because the United States is living in northern hemispheres. These lines, we call them lines of longitudes. Lines of longitudes. The lines of longitudes. These lines, this is 6 miles, by the way, okay? Because a township, it has 6 sections at the base, 6 by 6 is 36. But these lines, because the globe is like this, okay? We have, this is the North Pole, and this is the South Pole. And if you connect them with a line, and the lines of longitudes, they are running this way. We call them lines of longitudes. As we see here, as we go to the north, the distance is getting smaller and smaller and smaller. The distance between the lines of longitudes is getting smaller. So when they start with the standard corner here, which is SC, and they go to the north, they close here at a corner called a closing corner, CC. The closing corner, it does not have 6 miles. It is less. So in order to avoid having very small townships, what we do, or what they did, President Thomas Jefferson and his team during that time, they reset the corners and they start a standard corner here, SC. Every 4th township, they start over again by resetting the standard corner. Okay? So this is what is meant by standard corner and the closing corner. Let me take you to the picture, and after that we will look to the questions to see which one. But the picture is very important in order to make sure that you really understand. So this is the chapter 14, which, as I told you, it is the USBLS, United States Public Land Surveys. And I said that don't spend too much time. I needed to get the concept only and solve the problems on the back. This will be more than enough. You might be seeing a question directly or indirectly related to this topic. And here it is, President Thomas Jefferson on 1785. He is the one who started the US. Here it is. So if you look to this figure, which is figure 14.3, you will find the two lines I was referring to, which is the baseline. This one here, the baseline. This is the initial point. This is the initial, they're starting here. In California, you have three initial points, by the way. In California, you have three. So this is called the baseline, and this is the principal meridian. And we start with township as the 6 miles at the bottom. So after the fourth one, you will find that we do have two. We have something CC and SC, a closing corner and a standard corner. The closing corner, it is less than 6 miles. Okay, this is the closing corner here. The closing corner. You start here at the bottom, and you, because of the lines of longitudes, they are converging to the north. So we are getting, okay, a distance less. This is why after the fourth township, they set something called a parallel line. This is the first standard parallel north to correct that. This is called a correction line, by the way, also. It's called the correction line. We have to the north and to the south, by the way, because also we are going in both directions. So there are two definitions here about the closing corner and the standard corner. Okay, the question that you are referring to, my friend, and they are discussed here, by the way. They are discussed in my chapter. Let me show it to you. It is on page, at least to read more if you like to read more. It is on page, the textbook, and I believe you have it, page 334 of the textbook. Here it is. This is a closing corner, and this is the standard corner. So when I'm talking about the guide meridians and the difference between the closing corner and the standard corner is given here, but basically the standard corner is a corner where we have the township base is 6 miles, but the closing corner is at a distance less than 6 miles. Okay, so please read this section, Larry, and I will be glad to help you. But let's go to the question that you are asking and see what is the best answer for these two questions, 423 and 424. And always, I highly recommend you, when you read all 4 possible answers. Don't just be happy with the first answer and go home. No. Okay. So the standard corner, it governs the subdivision of the land laying between each standard parallel and the next standard parallel to the north. Govern the subdivision of the laying of land laying between each standard bearer and the next standard bearer to the south. So the difference between this and this is one to the north and one to the south. And is always 24 miles from the initial, or none of the above. The best answer is A, to the north. Because, as I told you, the standard corners, they started here and go this way. So the standard could go to the north. The closing corner is to the south. And this is why you'll find that the answer for 424, let me see. No, this is okay. So 223, 423 is to the north. No doubt about that. Let's read number closing corner, which is 424. Okay. And I will take this and enlarge it to show you the difference between. So here it is. This is a line, which is the standard barrel. I will put standard barrel. Standard barrel. So the closing corner is to the south. Here it is. This is a closing corner, CC. But as I told you, in order to eliminate or avoid having very small townships, we start here, but we go to the north. This is a standard corner. So the standard corner, the answer for this is A, and this one for B is the south. And this is the difference between the two corners, one to the north and one to the south. Okay, because this is going to the north of this standard barrel, and this is south of the standard barrel. And this is very obvious from the drawing. So the answer for 423 is A, because it's to the north, and the answer for number 424 is to the south, which is B as in boy, which is very clear from the drawing. Let me bring the drawing one more time. And here it is. Here it is. This is the standard barrel. First standard, you'll find that the closing corner to the south, but the standard corner is to the north. This is north of the standard barrel, okay, and this is to the south. So the closing corner to the south and the standard corner to the north of this reference line, which is first standard barrel. And this is always true, okay? Always true. You'll find that the standard corner to the north, and if you have the closing corner here will be to the south. So the answer for number 423, my friend, is B as in boy, and for number 424, for 423 is A, and 424 is B as in boy. I hope it's clear. Okay, good. So we are. So please let me know if there is any other question that you have. For those of you who are taking the exam very soon, let me know, and if I can squeeze any time to have additional help for you guys, I will not hesitate to do that. Otherwise, we are going to meet in the last session. But please keep me busy by sending something to me or prepare something for you. I know I'm extremely busy, but I'm saying that for the class. Please do your best, and I will do all my best. Okay. If you are taking the exam like Faisal taking the exam on the 21st, I wish you the best. If you have set of questions, please email it to me in advance. Simple email, and I will gather all these questions. At least I can look to them before I come. I don't like to waste your time, or if I need any additional equation from another source or something like that, I will be glad to help all of you. Okay, I will stop here, and thank you very much for coming tonight, and good night, everybody. Sorry, I have to stop here because, wait a second, some of you is raising the hand. Okay, let me see who is raising the hand. I didn't pay attention to that. Oh, you are very welcome, my friend. You are very welcome. Okay, but let me see who is raising the hand. Okay, Kaylee, okay. Let me see, okay. I hope I pronounce this. Go ahead, Kaylee, you are in there.
Hi, I was just wondering if you could go over the definitions. Can you hear me?
Barely I can hear you. The sound, can you get it closer? Go ahead, sir.
Can you hear me now?
Yes, much better, yes. Go ahead, please.
Can you go over the definitions of the variables in the vertical curve obstruction equation? They're kind of hard to understand in the book.
I lost again. Can you write the question? Can you write? I will wait for you until you write the question, because there is a background. For some reason, I am not able to capture every single word. Can you write the question for me, please?
Yes.
Is it possible, or you don't have access to the computer?
Yes, I'm typing it.
Yes, please. Okay, sure. At least I can understand the question, because okay, the vertical curve with obstruction equation. Oh yeah. Okay. In chapter 10 of my book, and I will show you exactly what I'm thinking, and correct me if I'm not capturing your question. Sometimes we have vertical curves where we have certain requirements for the vertical clearance, like this one here, a problem 1014. And this is probably what you meant by obstruction. Okay. We have a bridge, and the bridge has a gas line or a water line attached to it. And let me make sure that this is Kenny, okay. The variables in that equation are a little bit okay. That's fine. I will this what but just to make sure that this is the right concept you are looking for, and it seems to me this is the right concept. So this is the equation that available in. There are two equations, by the way. This is one of them, and there is another equation. I'll be glad to send it to you. I believe it's available on my second book, which is the let me see if I have a copy here of the summary of equations and topics. Let me see. Comprehensive summary. Yes, I have it here. So in this book, this is the one equation which I'll explain it to you, and the summary, comprehensive summary of equations and topics. If you go to chapter 10, you will find that I am providing another equation available also in textbooks. We can derive these equations, but nobody will ask you to derive any equation, as I mentioned before. Both of them are easy to follow. Here it is. This is the equation. I call it equation 10-33. Okay, which is this equation, the one here in the front of us, which I will go over it in just a minute, the parameters. And the second equation is given here. I call it 1033A. Both of them, they came from the same source, by the way, from the same derivation, but they are using different notations. So if you understand either one of them, both of them, they should give you the same answer. And I have some problems solved it using the two equations, and they give me the same answer. But for in the textbook, the problem shown on page 251. So it's giving you some kind of pipe. Imagine that this is a bridge, and the bridge, it does have some kind of a pipe attached to it, to the soffit of the bridge. I'm showing only the pipe. And we need to get a vertical curve to go under this pipe, such that we need to get a vertical clearance of a certain amount. So this is my vertical curve. Sorry, let me draw it a little bit better. To make it symmetrical. This is the vertex. So this is a vertical curve that's supposed to go under the bridge. Here it is, under the bridge. Such that this vertical clearance to be at least 16.5 feet. So I need a vertical clearance between the bottom of the pipe and the curve to be 16.5 feet. So this is one of the equations available in surveying textbooks. L is equal to times A plus bracket here 2 times offset over delta G plus 4 square root of A times offset over delta G plus offset over delta G square. Let us look to the parameter. What is A? A is the distance in stations from the vertex to the object. From here to here, this is A. So if I know this station and I know this station, the difference between them, like in this here, I have 10 plus 50, which is here it is, minus 8 plus 90, which is given for the station of the pipe. The difference between them is 1.6 stations. So the distance A is the horizontal distance between the vertex and the object. So I got the A. Delta G is the absolute between G1 and G2. So I take G2 minus G1. G2 is given and G1 is given. So I take the difference between 3.5 and minus. This will give me 6.5 because this is minus. So G2 minus G1 give me 6.5%. And I take the absolute value. I don't put the percent in the equation as well. I want to see. The third, so this is the second term. This is the A and this is delta G. The third term is called offset. What is offset? Offset is the tangent offset to the curve, which is the difference in elevation between the proposed curve and the tangent to the pipe. Tangent, okay? And tangent at the pipe location. This is the offset, by the way, we call it vertical offset, this one here. So let me call this point. This point here on the curve, I will call it Y1. And I will call the corresponding point on the tangent Y2. This offset, we call it vertical offset. In fact, this offset, by the way, in the equation, this vertical offset is the third term of the equation, which is Rx squared divided by 2, by the way. How can I get this vertical offset? If I can get Y1 and Y2, take the difference between them. So what is Y1? I know the elevation of the top of the pipe, and I know its diameter. So 114.5 minus 3 will put me here. Minus 16.5 will put me here, and this is Y1. Here is Y1. You see that? It is 114, which is the elevation of the top of the pipe, minus 3 feet, which is the diameter, minus 16.5, which is the vertical clearance. I need vertical clearance to be 16.5 feet. So this will give me Y1. What is Y2? Y2 is the elevation of a point on the tangent at the same station. So if I know the elevation here, 80.4, here it is, and I know the distance A, which is 1.6 station, and I know G1, so it is G1 times this, and this is the Y2. Take the difference between Y1 and Y2, give me 9.8 feet. After that, I took everything and plug it into the equation. Don't forget that 6.5%, we put only, don't put the percentage, it's 6.5. We don't put the percent, because we are going to get the answer in stations. So you plug all this into this equation, and here is the answer, 17.89. And he told you, express the answer in full station. Full station means that the answer B is out and the answer D is out. So the only two answers left, the answer A and the answer C. But 4 station means I'm rounding. So 17.89, when you round this, you round it to what? To 18 stations or 1800 feet. And this is the wrong answer. So if you pick the 18, this is the wrong answer. Even the rounding is correct. Because if you are going to get, if you are going to get 18, yeah, that's correct. I'm thinking in the right direction. If you get the 18, if this curve here is the 17.89 stations, this is a calculated one. Where is the 18? The 18 stations is above or below? It is above. The curve get longer. I'm just exaggerating. When this is the 18 stations or 1800 feet. If you are using 1800 feet, what's happening to the vertical clearance? You are getting closer to the pipe. And this is why rounding, you are completely right. Rounding 17.89 will give you 1800, but we don't use 1800, we use 1700 because 1700 is shorter. This will give you enough, and this is why I selected the answer A. And here is the explanation for this. It's a very good problem, and I hope that the parameters A and the offset and delta G are clear right now. Make sense? Okay, I hope that this is. So look at it again, and I hope that it's clear now. If not, I will be glad to discuss it next time. Any other questions or any other comments or suggestions or a criticism, as we call it sometimes, I call it a criticism. You are very welcome. Okay. Larry is 352. What is 352? Sorry, do you have a question here, my friend?
Yes, I don't be clear about the equation of give out for the outside equals Rx squared divided by 2, right?
Yes.
And what's out of representing? R and X.
Oh, this is okay. Do you remember the general equation for the vertical curve? Y at any distance x is equal y of the BVC plus G1x plus Rx squared divided by 2, the equation I wrote probably. So this is the offset, the Rx squared divided by 2 change, and x is the distance. And the R, but we don't know R, by the way, because R is equal G2 minus G1 over L. But I don't know L. We don't know the L yet. This we are solving for the L. But the parameters is given in the book. Okay, R is called the rate of change per station. You are very welcome. Let me see what Larry is asking. Hopefully that 352. I don't know what's the 352. Okay. Question number 3. Oh, 452. 452. In fact, this problem here, it is a very good problem, but you have the solution and I will go over it. This is one of the questions that given in one of the quizzes. Different datums were used to reference a flood level to a local street elevation as follows. Elevation of high water level is given to be this based on the local flood control district. And elevation of the street is 17.8 feet based on the city data. Elevation 00 is based on the flood control district, which is equal elevation 2.3 based on the national North American vertical datum of 1988, and the elevation negative 1.23 based on the city datum is equal the elevation 00 based on the North American vertical datum. So he gave you 4 statements. Statement number 1, statement number 2, statement number 3, statement number 4. You're supposed to draw each one in reference to whatever is. You're supposed to have a reference. Okay? Let me get my drawing very quick so at least I can save time. This is, by the way, in the set of quizzes or the question that I gave you. You need to start from somewhere. So different datums, and this is a little bit, by the way, sometimes very confusing during the exam. So the city datum is below the, if I put this as North American vertical datum of 1988, I draw a line. This is 00. Okay, so elevation of minus 1.23 based on the city datum is equal to the 00 elevation of 1988. So where is the city datum? Is above or below? So the city datum is here. This is the city. And this distance from here to here is 1.23 feet. Why? Because he's put a minus. Elevation of minus 1.23 based on the city datum. If this is the city datum, if I go down minus 1.23, I will hit 00 of the North American vertical datum. Do you agree with me? So we finish this. Let us look. Elevation 00 based on the local flood is equal to elevation 2.3 based on the North American vertical datum. So if I went up a distance of 2.3 feet, I will hit what? I will hit the local flood control. So local flood control, let me use different color. Here it is. Local flood control. Local flood control. So this is 2.3 above, because he said here it is. So the flood control 00 is equal the elevation 2 based on this. So I went up, so this is okay. So we are done with this. Let's look to this. Elevation of the street is 17.8 feet based on the city datum. Do I know the city datum? Yes. The city datum is here. So if I go up 17 feet, I will look to the street. So this is the street. So from here to here is 17.85. Do you agree with me? And finally, the elevation of the high water level is 18.93 based on the local flood. What is the local flood? Local flood is here. So I need to go 18.93. 18.93. Okay, so this is 18.93. This is the water. So if I need you to draw it again. I know. Let me sketch it very quick again on my here. You need to start from, for example, I started here from the North American vertical datum in AVD of 1988, and I start to reference the city. The city is here, city, and this here, the distance here is 1.23, and this is a 0, 0, by the way, for the 0 plus 0, 0, or 0.00. And after that, the local is above this by 2.3. So this is the local here. The local flood control datum. And we have the city or the street, sorry. I'm running out of color here, or ran out of color. The city is 17 with respect to the city. So I will go up 17.85 feet. I will hit the street. Okay. And finally, the water, which is going to be the determining factor. The water, he said that the water is 18.93 with respect to the local flood. So right now, I can tell right now, so if this is 17.85 and this is 2.3 and this is 1, so how much is that? Which is a 2.3 minus 1.30 minus, so this is 1.07. And he's telling me that the water with respect to this, with respect to the local, okay, and this is 107 here. That means that from here to here, okay, which is 17.85. This is one way, by the way, of doing it, 0.85, and I will subtract 1.075 minus. It cannot be 1.075. 2.30 enter, sorry. 2.30 enter, and 1.23 minus. It is 1.07. Here it is 1.07. Okay, which is the difference between this. So right now this is 17.85 minus 1.07. So this distance is 17.85 minus. I got this distance to be 16.78 feet. Okay, from here to here. Now I need to get the water right now. So the water is from the local, which is from here. I know this is 16, so I will go up from here. This is the water, and this is 18.93. This is the water level. So is the street going to be flooded or not? Is the street going to be flooded? How much? This is the question. Either flooded or not flooded. Is it flooded by this amount here? How much? 2.15? Which is the difference between, so this is water. So basically this drawing here is basically you need to start from a datum and start to build all other datums in relation to each other. Okay, So it's a good problem, and I hope that everybody got it. Okay. I wish you the best, all of you, and never give up. If you took the exam and you didn't make it last time, don't worry. Just keep studying and keep working hard and keep understanding the concept. I always stress the concept. The concept must be very clear and well understood to all of you, because exams are not easy, and I wish the best to all of you. And good night, everybody. And thank you. And let me. Bye-bye.